Welcome to the deep dive. Today, we're really getting into the hidden language behind, well, almost everything digital.
Yeah, the way information actually travels.
Yeah,
Music, data, you name it.
exactly. We're doing a deep dive into waveform analysis, signals, systems, the core stuff.
The real building blocks.
We've got some great source material lined up for you, looking at key functions, transforms, the essentials, really.
And our mission, I think, is to cut through the complexity, right?
Sure.
Make it make sense.
Get you those aha moments. Because honestly, understanding this gives you a shortcut to grasping so much modern tech.
Absolutely. And it's fascinating how these, abstract math ideas, they connect directly to things we see and use every single day. It's not just theory.
It's the foundation. Doesn't matter if you're super technical or just curious.
Right. It underpins almost everything.
Okay, so let's dive in. The very basics. These generic functions.
Yeah, the sort of alphabet of signals.
And the first key idea, may be a bit surprising, is that what's inside the brackets, like xt, that t's for time, you can swap it out, put alpha in there or anything else. The function's shape, its blueprint, stays the same.
That's a crucial point. The underlying behavior, the form of the function, is independent of the variable itself. It often represents something physical, like time or position.
But the math, the shape, works regardless. You can use the same function idea for sound pressure over time, or maybe temperature across a space.
Exactly. Same analytical tools for different phenomena. It's really powerful for analysis.
Okay, so keeping that blueprint idea in mind, let's talk about a really unique one. The delta function.
Ah, the impulse function. Yeah, this one's special.
How so? What's its deal?
Well, it's defined as being zero everywhere, except at one single instantaneous point,
Like a perfect spike.
a perfect spike.
Yeah.
So, delta T2 is zero everywhere except right at T equals 2.
And only a T2, nowhere else.
Nowhere else. And here's the kicker. Even though it's infinitely thin, its total area is always exactly 1.
Huh. Infinite spike, but area 1. It's counterintuitive.
It is. But that zero everywhere else thing, vital. It lets us model really sharp, sudden events, like hitting a drum or flipping a switch instantly.
A perfect impulse.
Precisely. It helps predict how a system reacts to one single kick.
Okay, that makes sense. Now, you mentioned its properties. I found the sampling property really interesting when I was looking into this.
Oh, yeah, that's a fantastic one. Go on.
So you take any regular function, let's call it xt, could be anything, varying over time,
Right.
and you multiply it by our delta function, say delta t2.
Good.
The result is still a delta function right there at t2. But, and this is the cool part, its height, its magnitude, is now exactly the value of the original function xt at that specific point. It becomes x2 times delta t2.
Yes, it's like the delta function acts like a probe or a snapshot. It perfectly samples the value of xt just at that one instant, t2, and it ignores everything else.
It really shows the difference between a function, which varies, and a number, a specific value. It plucks that one value out.
Beautifully put. And that sampling idea leads directly into the convolution property of the delta function.
Okay, convolution. Sounds complicated.
The math can be, but let's focus on the effect with the delta function. Imagine you have another function, yt. Think of it like a shape, maybe a little wave or bump.
Got it. yt.
Now, if you convolve yt with our delta function, delta t2,
What happens?
you basically pick up the entire shape of yt
Yeah.
and shift it. You place it down on the timeline
Shift it where?
so that its origin point, its t0 point, lands exactly where the delta function was, at t2 in this case.
Ah, so the delta function dictates the new location for the start or the 0 point of yt.
Precisely. It's not centered over t2, but its reference point t0 gets moved to d2. The whole function yt is just shifted.
Okay, that's a key distinction. Shifting the origin. Got it.
Mhm.
So delta is an instant spike. What about something that just turns on and stays on?
Well, for that you need the step function, often called a heaviside function, ut.
And that one's simpler.
Much simpler. It's just 0 for all negative time. Bang. Then at t of 0 it jumps up to 1.
And stays at 1 forever.
Stays at 1 for all positive time, just a step up.
Okay, makes sense. Spike, step.
Yeah.
What about waves, cosine and
The
sine?
statistics, yeah, definitely fundamental. And honestly, being able to just sketch them roughly is super helpful.
How so?
Well, cosine starts high, right? Starts at 1 at time 0, goes down to -1, then back up to 1. That full cycle happens over a period of 2.
Okay, starts at the peak, and sine.
Sine starts low, starts at 0, goes up to 1, down to -1, and back to 0. Also takes 2 for the full cycle.
So they're similar, just shifted relative to each other.
Exactly, at a phase by 2 or 90 degrees.
Now, if we see something like cos omega t,
Yeah.
How do we figure out its period and frequency from that omega?
Great question. The key is knowing that a cosine completes one full cycle when its argument, the stuff inside the brackets, equals 2.
Ah, because 2 is one full circle in radians.
Precisely. So you just set omega times t equal to 2. Then you solve for t, and that t is your period.
Okay, omega t equals 2. Solve for t.
Got it.
And frequency.
Frequency f is just the inverse of the period, f1t. Easy peasy.
Right.
Which brings us to a really, really crucial relationship you absolutely need to know.
Okay.
The link between that omega, which we call angular frequency, and f, the regular frequency in hertz.
What's the link?
Omega equals 2 times f, always. Omega 2/5.
Omega 2/2. Okay, so if we had, say, cos 4t.
Then omega is 4.
Yeah,
So
yeah.
using the formula, 4p equals 2/5. Divide both sides by 2.
F equals 2.
2 hertz.
Exactly. 2 cycles per second.
But why have both? Why omega and f seems redundant?
It's a good question. Think of it like this. Omega, the angular frequency, is sort of the natural language for the mathematics of rotation and phase, like how quickly something is spinning in an abstract sense. Radians per second.
Okay.
Whereas F, hertz, is cycles per second. That's what we often perceive more directly in the real world, like the pitch of a sound, how many times something repeats per second.
So one's better for the math, one's more intuitive physically? Kind of, yeah. Different perspectives on the same underlying oscillation. Both are useful.
All right. Makes sense. Let's shift gears from waves to pulses. The rect function, rectangular pulse.
Yep. Rect-T, capital T.
Yeah.
Very common in digital signals.
And the neat thing here, the source mentioned, its width.
Yeah.
Yeah.
This is elegantly simple. The
Right.
width of that rectangular pulse is just, capital T, the value in the denominator.
Seriously, just read it off.
Just read it off. If it's rect-T10, the pulse is 10 units wide. No need to memorize a formula for the width. It's baked right into the notation.
That is neat. A nice mathematical shortcut.
It really is.
Okay, one more fundamental function. The sinc function. Sinc.
Ah, SINC. Yeah. This one looks wavier.
Describe it.
It has a big main hump or lobe right in the center, and then it oscillates on either side, kind of like waves, but the waves get smaller and smaller as you move away from the center.
Okay, diminishing ripple effect.
Exactly.
Yeah.
And the really critical thing to remember about the sinc function, especially for avoiding mistakes,
Yes.
it's zero crossings, the points where it hit the horizontal axis. They happen at integer values,
Yeah.
1, 2, 3, -1, -2, -3, and so on, assuming it's sinc t.
Equally spaced integer crossings. Why is that so important?
Because scaling often comes into play with sinc functions, and knowing those integer crossings gives you fixed reference points. It helps prevent scaling errors when you're analyzing things.
Gotcha. Keep track of the integers.
Definitely.
So delta, step, cosine, sine, rect, sinc. That's quite the toolkit. What's the big picture for the listener here? Why care about these shapes?
Because they're truly the alphabet. Any signal, no matter how complex a voice, a piece of music, a Wi-Fi signal, can be thought of or mathematically constructed using combinations of these fundamental shapes and their variation.
They're the basic ingredients.
Yeah, the basic ingredients, yeah.
Yeah.
Understanding them is the first step to understanding any signal.
Okay. So we have the alphabet. Now, how do we, read the words? How do we understand what frequencies are inside a complex signal?
Ah, now you're talking about the Fourier transform.
The big one.
The really big one. Its whole purpose, its main job, is to take a signal in the time domain, how it changes over time, and reveal its frequency components, what frequencies make it up, and how strong each one is.
Like taking a musical chord and hearing the individual notes.
That's a perfect analogy, yes. The Fourier transform is like having perfect pitch for signals. It tells you exactly which notes frequencies are playing.
So what does, say, our simple cos 4t look like after a Fourier transform? We know it's 2 hertz. Is it just a spike at 2 hertz?
Almost. It's actually 2 spikes, 2 delta functions in the frequency domain.
2? Why 2?
One spike is at the positive frequency, plus 2 hertz in your example. The other is at the negative frequency, negative 2 hertz.
Negative frequency. What does that even mean?
It's a mathematical consequence, really useful in the theory. It comes from something called Euler's formula. You don't need to get bogged down in it, but Euler's formula basically shows that a simple cosine wave can be thought of as the sum of 2 complex spinning components, one spinning forwards, positive frequency, and one spinning backwards, negative frequency.
Okay, so the math needs both positive and negative to represent a real cosine wave.
Exactly. And the Fourier transform sees both those components. Each spike, by the way, has a height or area of 1/2.
1/2.
Yep, 1/2 at plus 2 hertz, 1/2 at -2 hertz. They combine to give you the full cosine wave back in the time domain.
Fascinating. Okay, quick side note. The sources mentioned using j instead of I for the square root of -1.
Oh yeah, standard practice in signals and systems and electrical engineering generally.
Yeah.
I is usually reserved for electrical current.
So if you see j, think imaginary unit. Got it.
Just a convention, but a consistent one.
All right. Now, you mentioned Euler's formula. Are there other, key relationships with the Fourier transform we should know?
Absolutely. A really fundamental pair you just have to know is the rect function and the sinc function.
We met them earlier, the blocky pulse and the wavy one.
That's them. The Fourier transform of a rect function, the pulse in time, is a sinc function, the wavy shape and frequency.
And presumably vice versa.
And vice versa. The Fourier transform of a sinc in time is a rect in frequency. They're a linked pair. It pops up everywhere.
Okay, rect becomes sync becomes rect. That's a huge one.
It is, and it leads directly to another incredibly powerful concept, maybe one of the most profound,
Lay it on me.
the expansion-contraction property, or sometimes called time-frequency duality.
Duality. Sounds important.
It really is. It states something quite beautiful. If a signal gets stretched out or expanded in one domain, like time,
So a longer pulse.
yeah, like a wider rect function,
Yeah.
then its Fourier transform, its representation in the frequency domain, must necessarily get squeezed or contracted.
So a wider pulse in time means a narrower sync function in frequency.
Exactly. And the opposite is true, too. If you squeeze a signal in time, make it shorter, sharper, its frequency representation spreads out.
Wider in time, narrower in frequency, narrower in time, wider in frequency. They're inversely related.
Perfectly put. It's a fundamental trade-off. You can't have a signal that's simultaneously very short in time and very narrow in frequency.
Wow. When I first got that, it clicked why, a sharp clap sound seems to have loads of different frequency components. It's not a pure tone.
That's precisely it. A short, sharp event in time must occupy a wide range of frequencies.
Give us a practical example.
Okay, think about digital systems, like a computer clock. If you have a slower clock rate,
Meaning the pulses representing ones and zeros are longer, right? Wider in time.
correct, the reg functions are wider.
Yeah.
Because of duality, their Fourier transforms, the sinc functions in the frequency domain, will be narrower.
And narrower in frequency means?
It means the signal uses less bandwidth. A slower clock naturally occupies less space in the frequency spectrum.
Ah, so that's directly related to bandwidth efficiency.
Absolutely vital. Understanding this duality is key to managing how much data you can cram into a communication channel.
So why should you, the listener, care? Because this duality is literally how engineers design systems to fit more movies, more music, more everything into the limited airwaves or cables we have.
It's the physics behind efficient communication. It's not just a neat trick. It's fundamental engineering.
Okay, incredible. So we have signals, we have ways to see their frequency content. What about systems? What happens when a signal goes through something?
Right. Now we're talking about how signals interact with devices, filters, channels, systems.
And the key operation here seems to be convolution again.
Convolution comes back, yes. It's central to understanding systems, particularly a common type called linear time invariant systems, or LTI systems.
LTI, okay. Now, we said we wouldn't dive deep into the math of convolution itself.
Right. Let's stick to the properties and effects, especially regarding LTI systems.
Yeah.
Remember our delta function convolution.
Yeah, convolving YP with delta T2 shifted YT, so its origin landed at T2.
Exactly. That shifting property is part of it.
Yeah.
Now, for LTI systems in general, convolution describes how the system's own characteristic, its impulse response, interacts with the input signal to produce the output.
So the system sort of smears its own response over the input signal using convolution.
That's one way to think about it, yeah. It's how the system modifies the input over time.
Yeah.
But doing convolution directly can be mathematically intensive.
Okay. Is there a shortcut? Like with the Fourier transform?
There is. And this is arguably the most important takeaway relating signals, systems, and transforms. It's a cornerstone principle.
Don't leave us hanging.
Convolution in the time domain is equivalent to multiplication in the frequency domain.
Wait, say that again?
Convolution, that potentially complex operation in time, becomes simple multiplication when you look at the Fourier transforms of the signals in frequency.
Whoa, so instead of convolving the input signal with the system's response in time,
You just take the Fourier transform of the input, take the Fourier transform of the system's response, which we call the transfer function, HHF, and multiply them together.
and that gives you...
The Fourier transform of the output signal. Multiplication in frequency equals convolution in time.
That seems dramatically simpler. Multiplication is way easier than convolution.
Way, way easier. This property is why engineers work in the frequency domain so often. It transforms a difficult calculus problem, convolution, into basic algebra, multiplication. It's a massive simplification for analyzing LTI systems.
So this transfer function, HF, basically tells you how the system treats each frequency.
Precisely. HNF is the system's frequency response. It tells you, for any given frequency f, how much the system will multiply the amplitude of that frequency and how much it will shift its phase.
So HF output F, input F, basically.
Exactly. Assuming input f isn't 0 at that frequency, it characterizes the system entirely in the frequency domain.
Okay, let's connect this. What happens if our simple cos4t signal goes into an LTI system? Remember, its Fourier transform was 2 spikes at +2 Hz and -2 Hz.
Right, so those two delta functions in the frequency domain, representing the input cosine, effectively probe or sample the system's transfer function, HF, at exactly those two frequencies, f + 2 Hz and MP f's 2 Hz.
So the system only cares about its own response at the frequencies that are actually present in the input?
That's right. The output signal's Fourier transform will still be 2 spikes at +2 Hz and -2 Hz. The frequency doesn't change.
Still 2 Hz.
Still 2 Hz. An LTI system never creates new frequencies that weren't already in the input, nor does it change the frequencies that are there.
But something must change, right?
Yes, the amplitude and phase of those output spikes will be different. The amplitude of the spike at +2 Hz will be the input amplitude, 1/2, multiplied by the magnitude of HF, evaluated at f2. And its phase will be shifted by the phase angle of HF at f2. Same logic applies to the -2 Hz component.
So the output is still a 2 Hz cosine wave.
Exactly. But its overall amplitude might be bigger or smaller, and it might be shifted slightly in time, which corresponds to a phase shift depending on what HF looks like at 2 Hz.
That explains so much. That's why my stereo amplifier makes the music louder or quieter, changes amplitude, but doesn't change the pitch of the notes, the frequency.
That is precisely the principle at work. The amplifier is acting as an LTI system, ideally, changing amplitude via its HF, but preserving the frequencies.
Mind blown. Okay, let's wrap this up.
We covered a lot of ground.
We really did. We went from the basic alphabet, delta, step, sine, cosine, rect, sinc, understanding their core shapes and properties.
Those fundamental building blocks.
Then we unlock the frequency domain with the Fourier transform, seeing how it reveals the hidden components and that crucial time-frequency duality.
Expand in one, contract in the other. A fundamental trade-off.
And finally, the huge takeaway about systems. Convolution in time is multiplication in frequency.
Absolutely. The cornerstone for understanding LTI systems, filters, how signals are processed. Knowing HF tells you everything about how the system affects different frequencies.
It changes amplitude and phase, but not the frequency itself for sinusoidal inputs.
Correct. Which leads to a final thought, maybe. How many systems, how many filters are acting on the information you encounter every single day, subtly changing its characteristics based on their HF, without you even realizing it?
From noise-canceling headphones to image processing on your phone display.
All applying these principles.
So next time you listen to something, watch something, even look at a screen, maybe think about those hidden functions, the Fourier transforms, the filtering that's happening constantly.
It's the invisible language shaping our digital reality.
Hopefully this deep dive has given you a much better grasp of that language. Thanks for joining us.